Okay, so today we are going to be continuing from lecture and studying periodic attractors. Right, so this is in keeping up with our theme of trying to understand the long-term behavior of our systems, but allowing us now to consider systems which naturally oscillate in the long term. Okay, so first let's remember what is an attractor. Right, so an attractor, right, is a set, let's call it A for attractor, right, in state space, such that there is a neighborhood around this set where if we start in the neighborhood, so if x of 0 is in this neighborhood, then x of t, right, approaches A, right, as t goes to infinity. Right, so what this means is we have some set, so let's say it can be a weird looking set, so let's say this is our set A, right? Then there's going to be some area around A, so let's say this is our neighborhood. So that if we start anywhere inside this neighborhood, so let's say this is x of 0, right, the trajectory for this point approaches A as t goes to infinity. All right, so this is what an attractor is, right? And then an attractor is periodic, right? So an attractor is periodic if it's a closed loop. And remember, these are also called limit cycles or stable limit cycles, but they all mean the same thing. Okay, so now let's look at the problems we are going to work on. Okay, so this first one should look familiar from class, right? So the idea is we have these two distinct predator-prey models. So the Holing-Tanner model and the Latka-Volterra model, which we've seen quite a bit already. Right? And what we're going to do is perturb these models. So we're going to do a predator removal in both, right? And then see the differences in what happens. So let's start with the Holing-Tanner model. So you can choose A or B, but just because it's going to be a little bit easier to draw, I'm going to do my predator removal at B. Okay, so we start with B. We're going to remove some predators. So let's say we end up at this point. Okay, and we want to know what trajectory are we going to follow. Okay, so remember, we think of trajectories as sort of surfing along the vector field, which is these little green arrowheads. Right, so if we draw this guy, we're going to go like this. And he's going to start looping around. Okay. Right, and so it'll look kind of like this outer blue trajectory, but maybe a little tighter. Okay, so now let's draw the corresponding time series. So let's make, we'll do the prey first, right? So let's say N, right, will be the pink line. Okay, right, so we're gonna start here. Remember, often the easiest way to draw the time series is to pick some points, sketch the points in first, right, and then connect the dots, right? So let's say we go 1, 2, 3 like this, and so, we're going to actually want to go all the way up to 6. So let's say maybe 3, 4, 5, 6. Okay, and so then for n, right, where we've started the trajectory is about at 2, right? Then we're going to increase until we're 4, and then we'll probably peak around 5. Right, and then we're going to start decreasing again. So we're going to come down, we're going to get back to 2, or we're going to get back to 2, and then we're going to go even further. So let's say we go all the way down to 1, and then we start increasing again, but we don't go as far out, right? So we end up with, maybe we're maxing out this time at 4, right? And then we decrease again. And so it's going to look something like this. And it'll keep going. Okay, and then we will draw our other variable, let's say in green. Right, so let's say the green will be the predators. Okay, and we do the same thing. Right, so we start really below 1. So we're going to ignore the units a little bit. Right, and then we increase slowly. Right. So let's say when the prey was at 4, predators are still going to be at just about 1. Right, when we peak here, we'll be just over 1. Right, and then predators are still increasing, right, but we end up probably around 3, 3. Right, so we probably cross right about here. Right, and then we slowly decrease again, but we only really come down to just above 1 this time. Right, and then we can keep going, right, so we end up something like this. These aren't perfect, but we can see the pattern. Okay, and then we can do the same thing with the Laca-Volterra model. So in this case, I think it'll be a little bit easier to draw if we start at A. Okay, so we remove some predators, and let's say we end up here, and then what happens? We get a much tighter loop. It goes around in this direction. Okay, and so let's do the same thing. So let's make tuna pink. All right, and so we start with kind of a low number of tuna, right? And then we start decreasing until we get very low. And then we sort of stay there, and then we increase, then we decrease, right? And we've seen these graphs before, so we don't really need to focus too much on drawing this particular one. It's in your book. For many of you, it's also in your study guides. Right, and so do something else. So the shark's starting off at its peak, but it's also decreasing, right? And it'll peak a bit after. So it'll look something like... Okay. Good. So now we have our time series, right? The important things that we really want to look at here, right, are what are the differences? Okay, so we can note that we have some sort of oscillation going on in both, right? But in the Halling-Tanner model, so let's go like this, HT for Halling-Tanner, the amplitude of the oscillations is decreasing. So it's not a perfect repeat. Right? Because we are approaching this stable cycle. On the other hand, in the Lotka-Volterra model, which we've seen before, right, once we perturb, we're on a new loop. We have periodic oscillations which do not change. Right, so we could say that this model remembers the perturbation. Of course, it doesn't actually have a mind of its own, right? So it doesn't remember perturbation, right? But once we poke it off a starting point, it never moves again unless we do something else, right? It stays on its new trajectory. Okay, so let's keep going. So now that we've reviewed some of the ideas behind attractors, right? Does a trajectory that approaches a limit cycle attractor ever reach the attractor? Okay, so the answer is, in short, no, unless you have a very odd fringe case. So there are some weird examples where it might hit the actual attractor, but most of the times it will just approach. Right, so no, right, the trajectory gets closer and closer, right, as time increases, but does not necessarily reach the attractor. Because we only approach A as time goes to infinity. Right. So this does mean that eventually we will be so close to our attractor that, we have no way of really telling them apart. So in real life, when you have to measure or count things, we'd get so close that we'd never be able to tell that we weren't on our limit cycle. So we can still use the limit cycle for modeling, but technically speaking, we haven't actually gotten there. Okay, so now, right, we're going to say we have a periodic attractor and there's a single equilibrium point inside. So this is what we mean by contains a single equilibrium point. So we have a point and we have some sort of periodic attractor. So let's say it loops like this. Okay, what kind of equilibrium point must we have? So we can figure this out by thinking about what it means to be a periodic attractor. Right, so this means if we start in a neighborhood of the point, let's see out here, we're going to get slowly closer and closer to our attractor. Right, we start in here, right, we're going to move towards it as well. Right, so this is what a periodic attractor does. Right, so that means, right, we start inside, we move away from the point and towards the limit cycle, towards the periodic attractor. Right, so the equilibrium point must be unstable. Right, and generally speaking, in this case, it will be an unstable spiral. Right, and we want to note quickly that it does matter that there's not another periodic attractor or anything else going on inside the point, inside the first one, because we could imagine a scenario where we had a point, right, and then we have our loop, but we might have other loops inside, right? And if we get the stability right, we could make the innermost one unstable, the middle one, or we need one more, right? We could make the innermost one unstable, right? So we spiral towards the point, then out, towards this guy, then in, right? And then out again, right? So this just says it does matter that there are no more extra attractors to deal with. Okay. All right, but the main point is this one, that the equilibrium is going to be unstable. Okay. So, moving on. A periodic attractor is also called a stable limit cycle. Right. So what should an unstable limit cycle look like? Okay, so let's say we have some limit cycle. So we have some loop trajectory, and it's going around like this. Okay, what should an unstable limit cycle look like? Well, this should mean we start near it and then we move away. So if we start close, we get further away as time goes on. So maybe we have something like this, and if we start on the outside, we move away as well. So we'd end up with something like this. And this would be an unstable limit cycle. Because in all of the small neighborhoods, right, there's points which spiral or move directly away from the loop. Okay. And then finally, so now we have an unstable limit cycle. So let's say this guy is our unstable limit cycle, and an equilibrium point inside, right? What kind of equilibrium point must this be? Well, it's going to be sort of an opposite situation to part A. So we can say here we have a point, it's going to move further away from the limit cycle. Okay. And then we start out here, it's moving away from the limit cycle, but that's less important. Right, and since there's nothing else inside our loop, right, this must be some sort of stable equilibrium point. And again, usually this should be a stable spiral. And again, it does matter that there are no other limit cycles inside the loop. And so you should work out for yourself sort of a counterexample. So find a way that you can put another limit cycle inside this loop so that the equilibrium point is different. It's not stable. Okay. So if you have more questions, please feel free to reach out to your TA or on Piazza or check out office hours. And then we will be done.